Hi guys, this is Dr. Ricardo. We are going to do the second video for chapter 16. This one is going to be on one idea, and that is the pH concept. So let me give you the definition of pH and show you how you're going to use it throughout the semester. So the first thing that you have to realize, this is from the class notes for chapter 16, page 7. So whenever you talk about pH, you need to make a small p and a capital H because taking the p of anything is going to be something that we're going to do over and over again. So we'll talk about that in a second. So again, small p, capital H. So pH is a measure of the strength of an acidic solution. So if you want to measure how strong the acid content is, you need to measure the hydronium ion concentration, right? H3O plus is directly related to the hydrogen ion concentration that's at equilibrium. So if you want, the best way to measure it is to measure the molar concentration of H3O plus. So we know anytime we put something in brackets, we're talking about how many moles per liter of that substance we have at equilibrium. So our big concept here is it's going to be very important to us to discuss the bracketed H3O plus, which means the molar concentration of the hydronium ion concentration once the substance is at equilibrium. Okay, so molar concentration of H3O plus. Now, these numbers are going to be very small, typically fractions, so something like zero point 0.1, 0.001, 0.000073 are going to contribute to the acid strength. So it doesn't take much hydrogen ion concentration to make something acidic. So in order to measure that, and not be carrying around huge exponents all the time, 10 to the minus 7, 10 to the minus 4, 10 to the minus 2, we are going to take the pH instead of just measuring the H3O plus. So the definition of pH is at the bottom of page 7. pH is minus the log base 10 of whatever the hydrogen ion concentration is in solution. So basically, I put the hydrogen ion concentration in here. Let's say it's 0.003. I take the log base 10 of it. You have to do the log base 10, and then that number is going to come out to a negative number, and then negative and negative will give you a positive. Most pH values are going to be negative numbers because the log of a small number is going to give you a negative. That's what this negative is for, to get rid of that negative sign. It's not impossible for a solution, a very acidic solution, a solution who has a stronger than 1 molar concentration of acid to have a pH with a negative value. So it is possible, but we're not going to see it very often. Okay, the other definition we want to make is if we're going to measure the hydrogen ion concentration, we're also interested in the hydroxide ion concentration. This is another term called POH, so again, small POH, and that's the minus the log base 10 concentration of the hydroxide ion concentration in solution. And we're going to find out in a few minutes that this statement is always true about a aqueous solution that's at equilibrium at 25 degrees Celsius. So that's important, right? Temperature is always plays a role. So we're going to do all of our reactions in this chapter at 25 degrees Celsius. So at 25 degrees Celsius, the pH plus the POH will always be equal to 14. So that means when one of these guys goes up, the other one has to go down. So for instance, if you have a solution that has a pH of 2, you know for sure that the POH of that solution is 10 to the, excuse me, is 12. So 2 plus 12 equals 14. If something has a pH of 0, that makes the POH 14. If something has a pH of 7, the POH must be 7 because 7 plus 7 is 14. The pH is 10, the POH is 4. You get the idea. Okay, this is the top of page 8. You can, you guys are familiar with the pH scale, but I want to show you how it's related to the POH scale. Again, anytime you have a solution that's at equilibrium, okay, a aqueous solution at equilibrium at 25 degrees, the following will be the case. Let's start out with a neutral solution. So this is a solution of water or a buffer, something that has a pH where the total amount of acid and base are equal to one another. So that's a neutral solution. So you knew this already, but the pH of a neutral solution has a pH of 7. So we know that pH plus pOH has to equal to 14. So um, 7 plus a pOH of 7 equals 14. So you can work your way down here all the way down to 0. This is a very strong acid solution. We'll talk about what the concentration is, but if the pOH is 0, excuse me, the pH is 0, the pOH has to be 14. So anything with a pH less than 7 is going to be an acid. Anything with a pH greater than 7 is going to be a base. The pOH works opposite. The same solution, so it's still going to be basic, but this time if you were worried about the pOH scale, when the pOH is very low, that's a basic solution, and when the pOH is very high, that's an acidic solution. So I have 3 reference points in here, 0, 14, 7 and 7, and 14 and 0, but you can fill in all the individual numbers here, like all the whole numbers. So if this guy's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, these guys opposite are going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So come over here and make this a pOH, excuse me, a pH of 6. This guy has got to be, um, this guy has a pOH of 6. This guy has got to be, excuse me, a pH of 6. This guy has to be a pOH of 8 because 6 plus 8 equals 14. So you can do that in every case. Okay, so 2 facts that we're going to talk about. We just and the rationale for why is we just said that the pH of any solution at equilibrium at 25 degrees plus the pOH is equal to 14. Well, the reason that exists is because this statement is true. If you take the p's off and just look at the original concentration, it turns out that in any aqueous solution at 25 degrees, the hydrogen ion concentration multiplied by the hydroxide ion concentration is always going to be 10 to the minus 14th. So not only is this true, this statement is always true. I'm going to show the origin of this in a minute. It has to do with the autoionization of water, which we talked about a little bit. And then from there, we can go from here and derive this. So I'll do that for you. Okay, so this is actually the real scientific fact down here. And I'm going to show you where it comes from. And then this is a sort of a man-made way of looking at it, where we take the log of everything. We basically take the log of this number, take the log of this number, and take the log of this number. So I'll show you that in a second. Okay, so that being said, let me show you where this fact comes from, that the hydroxide ion concentration times the hydronium ion concentration is always equal to 10 to the minus 14th. Okay, so that comes from a reaction that we already talked about that turns out to be an equilibrium reaction. It's the autoionization of water. When 2 water molecules react with each other, so you can either write it water molecule plus water molecule, or obviously you could replace that with 2H2O liquid, right? Goes to hydronium and hydroxide. We said that this reaction occurs because one water molecule hits into the other water molecule. Let's have the first one donating a proton to the second one, right? So that would mean that that first one would wind up as hydroxide, and then this one would wind up as hydronium, if this is the guy who's capturing the extra hydrogen. So this is a conjugate acid-base pair. This guy would wind up with this one would wind up with that one, and you could label everything. So typical conjugate acid-base pair. Well, it turns out that the equilibrium constant for this reaction is the products divided by the reactants. So you have the concentration of hydronium times the concentration of hydroxide in the numerator, and you would ordinarily divide by the products. So why do we leave water out? Because I told you in the last chapter, in chapter 15, that we always leave out condensed matter, which would be any solids or liquid water. Because if we did include it, we would just have a 55 squared down at the bottom because the concentration of water in water is always 55. It's hard to make it move from that. So basically, since that never changes, we just, as a convention, always leave out the water from the left-hand side. So this equilibrium expression, which we talked about a lot, this equilibrium expression is given a special name. It's not only Kc, we're going to call it Kw. Kw is going to be the autoionization for water. Okay, we're going to save that K small w just for this reaction. Okay, and Kw, if you do the experiment, turns out to be 1, this is a 1.0, times 10 to the minus 14th at 25 degrees. It varies a little bit as you change the temperature. It's not going to change much, but we're going to do all of our acid-base chemistry at 25 to keep it simple. Okay, so we know that Kw is equal to H3O plus times OH minus 1. Some people call that the ion product of water. So let's take a look at an example here where we talk about trying to figure out, well, what is the concentration of hydroxide and hydronium in a solution of pure water? So that's what this example is here. What is the concentration of hydronium and hydroxide in water at 25 degrees? Okay, well, the interesting thing is we don't even really have to make an ice table, right? Because we only have one variable here. We know that water has an equivalent amount of hydronium as hydroxide. And actually, if we made an ice table up here with this original reaction, you would see that you'd start with 55 moles of this and 55 moles of that, which is such a huge number of initial concentrations here. And I'd wind up with X of this and X of this. So I could do it from an ice table or not. This is going to turn out to be X, and this is going to turn out to be X. Why? Because the stoichiometry is 1-to-1. Every time you create a hydronium ion, you have to create a hydroxide ion. Why? Because we only have pure water. There's nothing else in the solution. If I start dumping in an acid or a base, then that's going to contribute to other reactions to cause hydronium and hydroxide. But we don't have that. We just have pure water. Okay, so if you come down here, at equilibrium, right, in a pure water sample, this is going to be X and this is going to be X. So what we wind up with is X squared is equal to Kw. And we know the value of Kw has been experimentally determined to be 1 times 10 to the minus 14th. So if X squared is 1 times 10 to the minus 14th, what's X? The square root of 1 times 10 to the minus 14th. And the square root of 1 times 10 to the minus 14th is 7. So going back up here, not only is X 1 times 10 to the minus 7, we can plug that in. It's the equilibrium concentration of hydronium and hydroxide. So we've just figured out in a pure water sample, we have this concentration of hydronium and this concentration of hydroxide. Well, let's take the log of those two numbers. If you remember, if you want to get the pH of something, you would take the log of this and then drop off the negative sign. So I'm going to do that on a piece of scrap paper, right? So the question that we have is, what is the log of 10 to the minus 7? So right now, we know that the hydronium ion concentration is 1 times 10 to the minus 7th. And then down here, the hydroxide ion concentration is 1 times 10 to the minus 7th. We just figured that out from the autoionization, right? Again, we have just pure water. We know these are equal to each other. Okay. So next thing, the definition of pH is pH is equal to minus the log base 10 of whatever the hydronium ion concentration is. Okay, so let's plug this number in here. So we need minus the log of 1.0 times 10 to the minus 7th. Okay, well, you can try this on your calculator. Take the log of 1 times 10 to the minus 7th. But what you'll realize pretty quickly with log base 10s is if you have just the number 1 here in the mantissa and everything is in the exponent, the log of 1 times 10 to the minus 7th is going to be minus 7. So when I do that, I'm going to get minus 7. So I'm going to have a minus 7, which is going to be equal to 7. So we just learned something that we already knew, okay? And that is the pH of a neutral sample of water is equal to 7. Let's do the same thing with OH. We're obviously going to get the same result. The definition of POH is take minus the log base 10 of whatever the hydroxide ion concentration is. Okay, plug that in. We need minus the log base 10 of 1 times 10 to the minus 7th. If you don't believe me, please go ahead and punch it in your calculator. Put log, open parentheses, 1 e minus 7, close parentheses. When you do that, you take the log of this number, you're going to get a big fat minus 7. And on purpose, whenever we p something, we take minus the log of it. So minus the minus log also gives us 7. So not only is the pH 7, the POH 7. POH is 7. You can get this in any of those cases that we talked about. If the pH of something is equal to 8, it means the hydronium ion concentration, you'll get used to this, right, is equal to 1 times 10 to the minus 8th. You can do this in your head whenever it's a whole number like this, so 8.0. Well, if this is 8.0, then we know that POH has to be 6, right? Because 6 and 8 is equal to 14. So when I add those up, I get 14. Okay, so if this is 6, then the hydroxide ion concentration is going to be 1 times 10 to the minus 6. Don't believe me, just go backwards. Okay, and interestingly enough, the pHs and the POH will add up to 14. The hydronium and the hydroxide will multiply. This side is adding because we took the logs of them. This side is multiplying. Okay, actually I shouldn't do a double line. Double line means add. I'll do a single line. If we multiply this, 1 times 1 is 1. 10 to the minus 8th times 10 to the minus 6th is 10 to the minus 14. So we just proved that multiplying the hydroxide to the hydronium will always give you Kw, which is 10 to the minus 14th, and adding pH plus POH will always give you 14. So one of the things that you can do is you can make a little table to go around in a circle. So if you have any aqueous solution at equilibrium, the following will be true. So I have an aqueous solution at equilibrium. Okay. Anytime I have an aqueous, sorry about that. I have an aqueous solution that's at equilibrium. Okay. And I better make it at 25 degrees so that we can use the 14 number, not have to look up what Kw is at a different temperature. So at 25 degrees Celsius, I have an aqueous solution. Okay. It's sunny today, guys, so I'm getting a little glare from the outside. Let me see if I can do this. All right. I'll just move over here out of the glare for you guys. How's that? Okay. All right. So look what's going to happen. Let me see where I want to put everything. Let's put pH over on this side. Okay. So anytime I know the pH, right, I can definitely, I'll make these guys diamonds, okay, to make them nicer. I can get the hydronium ion concentration, right? How do I get from here to here? Well, I get from here to here, or let me go back first. I get from here to here by taking what the pH is. So if I go from here to here, I have to take minus the log of hydronium ion concentration. Okay. How do I get from here to here? I have to take 10 to the negative pH. So I'll give you an example. If the pH is 3, 10 to the negative 3 will give you the hydronium ion concentration. Okay, so this goes from here to here. Okay, so now down here, I'm going to get to my other partner, right? POH. So POH I'll put in a diamond too. Oh, you can't see that. How's that? Go backwards a little bit. Good. Okay, how do we get from here to here? Well, these are related through this fact. pH plus pOH is always equal to 14. So if I know this, not only can I get hydronium ion concentration, but I can get pOH. So again, let's do as our example of 3. If the pH is 3, then we know the pOH has to be 11. Okay, so how can I write that? Going this way, it's going to be 14 minus the pH. So 14 minus 3 will give you pOH. Going this way, it's going to be 14 minus the pOH. Okay, so 11 minus, 14 minus 11 would give you 3. Okay, all right, one more player. Who's on this side? You know what? Since I put pOH in a box over here, let me put pOH in a box. This way I'm even. All right, so this guy will be in a box, this guy will be in a box. How's that? Good. All right, so that makes this dude a diamond. So the diamonds I'm going to multiply, the boxes I'll add up. Okay, so where are we? Right, our example was 3, pH equal to 3. So we said if pH is equal to 3, this is 10 to the minus 3. If the pH is equal to 3, this makes the pOH equal to 11. Okay, so I'm going to put in all the numbers now. I can actually put it now. So for our example, this is 3, this is 11, and this is 1 times 10 to the minus 3. So anytime I know any of these 4 numbers, I can calculate the other 3. Okay, let's get from here to here. Okay, how do I get from here to here? This guy's OH. Okay, so I have to do this. If I have the pOH and I want the hydroxide ion concentration, I have to do the same thing I did over here. I have to take 10 to the minus pOH. So let me give you our example. Our example was a pH of 3, right? So the pH is 3. Right now I know pOH is 11. So 10 to the minus 11th will be the pOH concentration. Okay, this is 10 to the minus 11th. 1 times 10 to the minus 11. Again, you're only doing this in your head when these are nice and easy numbers like whole numbers like pH equal to 3. Okay, all right, so down now, this guy's 11. Okay, this is 10 to the minus 11th. Okay, how do I go from here to here? I take the negative log of the hydronium ion concentration. Kind of like this example up here. So take the negative log of 10 to the minus 11th. The log of 10 to the minus 11 is negative 11. Negative times negative 11 gives you 11. Okay. All right, last step. How do I go between here and here? These are the two that are multiplied together. So I have KW, right, which is 10 to the minus 14th divided by the hydroxide ion concentration, which I just figured out, will give me the hydronium ion concentration. So let's see if that makes sense. 10 to the minus 14th divided by 10 to the minus 11th. 10 to the minus 14th divided by 10 to the minus 11th gives me 10 to the minus 3. All right, how do I go from here to here? I take 10 to the minus 14th is going to be in the numerator. I'll show you that in a second. Divided by the hydronium. Okay, let's make sure that's right. So 10 to the minus 14th divided by 10 to the minus 3 is 10 to the minus 11th. Okay, so you can make a little box like this and work your way around using our two formulas, right? And our two formulas are this one, Kw, which has a value of 1 times 10 to the minus 14th, is always equal to the hydronium times the hydroxide. So if I do a little algebra, I get both of these guys up here, right? This one, when I wanted to go this way, I wanted hydronium, so I said hydronium is 10 to the minus 14th divided by hydroxide. When I wanted to go this way, I said I want hydroxide, so I took 10 to the minus 14th divided by hydronium. So these two things over here are just the algebra done on this. And what's our other fact that we know? So this is fact number 1 at 25 degrees. Fact number 2, 14 is equal to pH plus POH. So I'm going to do the derivation for that in a minute, but you don't have to know that. These are going to be your two facts, okay? Any one of these four values up here, if you know one, you can calculate the other. Okay, let me give you a very basic solution. If I have a basic solution whose pH is 10, right? So if the pH is 10, the hydronium ion concentration is 10 to the minus 10th. Okay, so this is 10 to the minus 10th. That makes this 10 to the minus 4th, and that makes this 4. So I would get a 10, a 4, 10 to the minus 4, and 10 to the minus 10th. See how in a basic solution whose pH is 10, I'm going to get much more hydronium than hydroxide. These are going to be opposite. Okay. Here, I have an acidic solution whose pH is 3. I've got a lot more hydronium than hydroxide. I think I said that right. Okay. So practice this. This is the easy part, right? Manipulating these two equations. Good. All right. Last thing. Let me just derive the POH statement for you. Okay, so we know in a solution of any aqueous solution, right? It doesn't have to be pure water. Any solution will come to equilibrium because of the autoionization reaction. These two reactions are incredibly fast, and within seconds, the equilibrium will be reached. So we know that this is always true then, right? Uh, P, excuse me, Kw is always equal to hydronium times hydroxide. So this is true even at other temperatures because Kw, all equilibrium constants can change. But if we make it specifically at 25 degrees, we know the value of Kw. Okay, so in that case, the value of Kw is 1 times 10 to the minus 14th. Okay, so now we're specifying at a specific temperature. Again, it doesn't change dramatically, but once we're at 25, we can put the number in. Okay, well, let's take the log of both sides. So if I take the log of this, I get the log of 1 times 10 to the minus 14th is equal to, let's sharpen up a little bit. Pretty good? I got a little better. Well, if I take the log of that, I can take the log of this. So I'm going to do it in 2 steps. Okay, take the log of the whole thing. Okay, well, one of the rules of logs is the log of something multiplied by another thing is the same as the log of the first thing plus the log of the second thing. So that comes from the rule of logs. Okay. Now we know, oh, let's do one more step. Let me take the negative of everything. Let me multiply everything through by -1. So if I multiply through by -1 minus the log, okay, it's a free country, I can do that. And this one minus the log plus minus that one. So what I did is I factored out, better way to say it, I multiplied through the -1 by both of these. Okay, so because I want that plus sign on the outside. So I'm pulling the negative in here, right? Good. Okay, take a second with that algebra for that. Now I have a couple definitions right here. That's the definition of pH, isn't it? Minus the log of the hydronium ion concentration, that's pH. And inside the parentheses here, that's the definition of POH. So See, the negative sign is I got to take it in, fold it in to POH because that's the definition of pH. So look back a page and see that. Now I have this guy plus this guy. Okay. What's the log of 10 to the minus 14th? Minus 14th. Negative times a negative 14 gives me 14. So this is just the same thing as this, only in the log form. Nothing special about it. Okay. So this page right here, don't have to memorize it. You just have to know this fact and this fact. You don't have to memorize the derivation, how you get from one to another. Okay. This is just convenience for us because otherwise we'd be saying 10 to the minus 10 to the minus all day long. Okay. And it makes it much easier to just refer to a solution and say its pH is 3 than tell everybody the hydrogen ion concentration is 10 to the minus 3. Okay. And remember, a long time ago, people didn't have nice, easy calculators. So by putting things in the log form, it saved them a lot of math. Okay. Okay. Well, that's it for this section. This was the second section of chapter 16.